All right, so this is section 4.8, part 3, and we're going to take a look at the idea of differentials. It's a different way to use a tangent line to a curve rather than to approximate the actual y value. This would be a way to use a tangent line to approximate the change in the y values for a corresponding known change, a small known change in an x value. Basically, what we're looking at here is we're looking at a situation like this. Now, I know this graph looks complicated, so let's just break it down. First things first, we have a function f that is a differentiable function. Somewhere on that curve is a known point cf of c. So it is a value c for the input x and a value f of c for the output y. C is going to change by a little bit. Now in this picture here, the little bit is this delta x down here. So C is going to change from C to C plus delta x. So C is going to increase or decrease. This picture has it showing C as increasing, but we could just as easily draw this picture going in the other direction and have delta x be a negative value. It really doesn't matter whether delta x is a positive value or a negative value, but basically what we're going to do here is we're going to change C by a little bit. So C would be like 2 and delta x would be 0.1, so it would go from 2 to 2.1. Or C could be 5 and delta x could be 0.06, and then we go from 5 to 5.06. It just needs to be a small change in the x value. So C becomes a little bit bigger or a little bit smaller. Okay? And what we would really like to know is we'd really like to know how much does y change by when it goes from here up to there, because that would be the actual change in y. That would be the change in y. And this is what we want to know. But for whatever reason, the function f is a difficult function to work with, and we don't want to calculate it directly. We don't want to actually plug in 5.06 or 2.1 into the f function and evaluate it. So the argument that we're going to make is that this little tiny change here on the tangent line, as long as delta x doesn't move us too far away from c, that little tiny change in the y value of the tangent line is going to be sufficient for an approximation of the true delta y. And what that little tiny change in the tangent line is going to come out of is it's going to come out of our equation for our tangent line. Right? And I want you to look a little bit deeper into here, and I want you to see if you can see a triangle here. A right triangle here, where the horizontal is delta x, okay? And then the vertical here, we're going to call that our approximately delta y. That's the approximation we want to get. And so how are we going to find that? Well, the blue tangent line right here, we can find the slope of the tangent line. The slope of the tangent line is the value of the derivative over there at the good point C. And if the slope of the tangent, f prime of c, that's our m, is equal to the change in y divided by the change in x, and we know that the change in x is delta x, then with a little bit of algebra, we can multiply to get rid of that denominator. We can say that the change in y, the approximate delta y, is going to be f prime of c times our delta x. Now please forgive me because this is horrible notation here, right? But we're trying to approximate delta y. the approximation for the delta y is going to be f prime of c delta x because of that triangle, because of the slope of the tangent line. Okay. Now, how is this different from what we just got done doing in the first two parts of this section? Well, in the first two parts of the section, and let me erase a bunch of stuff here that we don't need. Okay. In the first two parts of this section, we wanted the y value at that new point. And so we would use the tangent line and find the approximation. In this example, we don't want the y value. We want the height here. We want the change in y, not the y, the change in y. And if what we want is the change in y, we can make this work. Now we make some changes in our definitions down here, and we say that if we let delta x be represented by the differential dx, and if we let delta y be represented by the differential dy, then we can say that the differential dy is equal to f prime dx. And what this is coming from is it's coming from this argument, that the derivative multiply and then we make the argument that dy is a good approximation for our delta y if dx is exactly our delta x. Okay. All right, so let's see if we can make, oh, I see an issue. Look at that. That's terrible. Why didn't I get that fixed? I'm going to pause this video, go fix that to make sure the one that you upload is correct. All right, you didn't see it, but I paused for about 5 minutes, went and found the file, changed the file, uploaded it, so the one that you have will look more correct, not ugly like that. All right, let y equal x squared. Find the differential dy when x equals 1 and dx equals 0.01. Compare this value with the actual true delta y for x equals 1 and a delta x of 0.01. All right, so let's take a look what's happening here. I'm going to make a quick sketch and see if I can figure this out. There's my function y equals x squared. If x is equal to 1, then that's my value c. So I'm looking at a known point right? And then x is going to change by a little bit. Now I am going to exaggerate it. This is definitely not to scale, right? Now if I zoom in on this, do you see the triangle that we can make? We can come in here, we can draw in a tangent line. Okay. We can draw in those two other sides of this triangle. This side down here is our delta x, which is the same thing as our dx. This side over here is our dy, okay, which is our approximation for our delta y. If you really want to know what delta y is, whoa, I don't like that at all. Delta y is this entire distance right here. That's truly delta y. That is the actual change in y. We're going to use this as an approximation for it. Okay? And then what does the definition say? Well, the definition says that dy is equal to f prime of the fixed point c times our dx. Okay? So first things first. What is our function f of x? Well, our function is y equals x squared, or f of x equals x squared. So then the first derivative, f prime of x, would be 2x. C is 1. Differential dx is 0.01. So then our differential, putting that all together and plugging all of that into that formula, we're then going to get that our differential dy is going to be equal to 2 times 1 times 0.01, or 0.02. That the approximation that delta y is approximately 0.02. Okay? Now what they want us to do is they want us to compare our approximation of 0.02 with the actual value. Okay? Well, the actual value, delta y, is going to be f of 1.01 minus f of 1. If I want to find that pink, I need to take the y value up here and subtract off the y value down there, and that's going to give me that pink. Well, the y up top is the function at 1.01. The y down the bottom is the function at 1. So that's 1.01 squared minus 1 squared. Okay? And I'm going to use a little trick that I learned a long, long time ago. This is a squared minus b squared, right? So this is 1.01 minus 1 times 1.01 plus 1. Yes, no, maybe? A squared minus b squared is a minus b times a plus b. Do you see a minus b sitting there and a plus b sitting there? Okay. 1.01 minus 1 is 0.01 times 2.01. Well, 2.01 times 1 is 201. And then I need how many 4 decimal places? So 1, 2, 3, 4. 0.0201. So the actual delta y is 0.0201. Our approximation is 0.02. We're off by, what is that, tenths, hundredths, thousandths? We're off by 1/10,000th. 1/10,000th off. Is that a lot? I don't know. Who am I working for? Okay. Am I building tools for Harbor Freight? Well, then off by 1/10,000th doesn't matter. Am I building tools for NASA? Well, then off by 1/10,000th might matter, and I might want to find a more accurate way to do this. Right? But either way, I'm pretty happy that I can be as close as 1/10,000th. Right? Sometimes this technique is used to find error. Right? Imagine that you're measuring the radius of a ball bearing, and you measure that as being 0.7 inches, as shown in that picture right there. So you have one of those calipers that measure that. I forget what they're exactly called. They have a fancy name, I'm sure. And you measure the radius as 0.7 inches, but you know that you might be off by as much as 0.01 inches. Right? If your measurement for your radius is off by as much as 0.01 inches, how much propagated air could be in the volume of the ball bearing? Now, just to be clear, are you comfortable with this phrase, propagated air? Right? Basically, the idea of propagated air says, if you use an incorrect measurement in a calculation, the error in the measurement, the error in that initial value that you put into that calculation will then make that calculation wrong. And that change or that error in that calculation is now called a propagation error or a propagated error. All right, so let's look at what's happening here. I'm measuring the radius. I'm off by a little bit. How does that affect the volume? So essentially, this is the problem we just did. I have an input value that goes into a function, in this case a volume function. That volume could be as off by as much as a delta, in this case a delta R. Okay? So I have an R of 0.7 inches. I have a delta R, which we're going to call our differential dr of 0.01 inches. And the question is, what does this do to V? What is the potential error in volume? Right? Well, if dy equals f prime of x dx, then substituting for the values and for the variables in this formula, dv should equal v prime of r dr. Or, more specifically, dv should be equal to 4 pi r squared times our differential dr. Now, if you're wondering where this came from, that's just v prime. Take the derivative of that function. Derivative of 4/3 pi r cubed is 4 pi r squared. Now, as a side note, something you may have noticed, the derivative of volume is surface area, because the surface area of a sphere is 4 pi r squared. The volume of a sphere is 4/3 pi r cubed. You'll learn more about that in Calc 2. All right, so now we're going to plug in our values. Our differential dv is 4 pi times our measured radius of 0.7 squared multiplied by our 0.01. Let's see. I'm going to use a calculator for this, so let me bring up my calculator. And I get, let's see, clear. Let's see, 4 times pi times 0.7 squared times 0.01 means that my volume could be off by as much as 0.061575216. Round that wherever they would tell me to round that. Right? Now, let's see, since this is a change in volume, then this would be, since I'm measuring in inches, inches cubed. And if you're wondering why inches cubed, those were inches right there that got squared, so that's inches squared. Those were inches right there, and inches squared times inches is inches cubed. Or volume is measured in cubic inches for this problem, so a change in volume would also be measured in cubic inches. All right, but often error is converted to relative error so that we can talk about it more correctly. And the reason that we turn error into relative error is a problem that exists within math with how big is a number. All right, so let me give you an example. Is $100 a lot of money? Well, it depends. If you're buying a new car and you've got it narrowed down to 2 different cars and the difference in price is $100, then $100 is nothing, right? If you're buying a new cell phone and you've got it narrowed down to 2 different ones and the difference in price is $100, well, now we're talking about some money, right? If you're buying a new pair of jeans and the difference in price is $100, now we're talking about a lot of money. So 100 can be a small number or can be a big number. Okay? So what we often do is we take error and turn it into relative error, because relative error is a percent of the expected measurement. And the way that we find relative error is we take the dy and divide it by the y. So what we're saying here is we're taking the change in y and divide it by the original y. So for us, we're going to take, because the example we're going to do is we're going to calculate the relative error in the ball bearing problem, is we are going to take this error that we found and we're going to divide it by what the radius would have been if this calculation would have been perfect, meaning if there had been no error in the measurement of the volume. So for us, we're going to say that since relative error, by definition, since our relative error is going to be approximated by the differential, right? Actually, I shouldn't write it like that. I should be more precise. Is the true change in y divided by y, which we're going to approximate by our differential divided by the y. And then so for our example, that means that our relative error is going to be the dv divided by the v. Now, I already know the dv. It's this horrible number right here. But I don't know v. So I'm going to have to find v. And it's V of 0.7 because it's the volume if there had been no change in the input. If the measurement of 0.7 inches for the radius of that sphere would have been perfect, and that's going to be 4/3 pi r cubed. So that's going to be 4/3 pi times 0.7 cubed. This is a calculator problem. So I'm going to go ahead and bring the calculator back up. And so then I'm going to say, okay, well, what is 4 divided by 3 times pi times 0.7 cubed? That's going to be our denominator. So that is this value. The 0.06 is the numerator, this value. And so then I'm going to get, let's see, what is that going to be? That's going to be divided by, and I get that our relative error is 0.04285711429, or approximately 4.3%. Is 4.3% a lot? I don't know. Depends on what I'm making these ball bearings for. Are these ball bearings going into the International Space Station? Are these going to go in, ball bearings be used on our next trip to Mars? Then being off by 4.3% is way too much. I can't accept that. Or are these ball bearings going into a caster on the bottom of a tool chest that they're going to sell at Harbor Freight? Well, then if my volume measurement is off by 4.3%, I don't care. Close enough, it'll fit, it'll work. It can be off by that much. But to me, 4.3% means so much more than 0.061575216 cubic inches. I can actually look at this and say, okay, 4%. I can either accept or I can not accept a 4% error. All right, that brings us to the end of section 4.8. I think this means we're going to have an exam over section 4.7 and 4.8, so good luck on that exam.